Hello, welcome back. Today we're going to talk about growth and decay. This is a continuation on what we've been talking about in terms of solving differential equations. Matter of fact, let's take a look at the first example. It's just a review. We want to solve this differential equation right here. dy dx equals 4 minus y. We're going to be doing a lot of these today, so let's go and take a look. So the first step we have to do, of course, we have to separate out the variables. So when we do that, we're going to bring the 4 minus y over to the left. Not just the y, but the 4 as well. So we would get this 1 over 4 minus y dy equals, and over here on the right side, we're going to multiply by that dx. When we integrate, this is going to become the, oh no, we got u substitution. So we get u equals 4 minus y. Du is this negative dy. Give me dy is negative du. That's negative that we want. I'm going to rewrite over here. This becomes the negative 1 over u du equals the integral of just dx. Integrating, we get the negative natural log of u equal to, and if we integrate the dx, that's just going to give us x plus c1. We don't want this negative right here, so we're going to divide everything through by it, and that's going to give us the natural log of u equal to negative x plus c2. Now remember, we're just taking this negative c1 and we're just calling it another constant because this constant will just absorb. And when we exponentiate, we would get this natural log, the natural log disappears. Here, don't forget the natural log disappears, so those cancel, and we're just left with the absolute value of u, and I'm going to go ahead and sub my u back in. 4 minus y equals, and now we have that little algebra rule that we have to do here. So you might remember, so we're adding the exponents here, so what we're going to do is we're going to write this as the product of two exponential functions with the same base. So we get e to the negative x times e to the c2, and then we're going to say let c e to the c2 equals some c3, some random constant there again. And what we're left with is this 4 minus y equals, put the c3 first, and we're going to put a plus or minus because we're taking that absolute value, e to the negative x. And there we have it. We're going to do this a lot today, so all right, let's take a look. Before we begin, though, we have to redefine some words from pre-cal last year. The first one is direct variation. Direct variation occurs when, in a growth or decay, when we are what we call directly proportional to a certain constant. Now, we don't know what that constant is, so we just call it the constant of proportionality. We typically use the letter k. For example, a line is a direct proportion. We have y equals kx. I could also write this y over x equals k as well. Inverse variation is when the constant of proportionality is divided by the variable. So now, for example, here I get y equals k over x, or xy equals k. This is more like your irrational function. So where this is considered like our linear function, inverse variation is our rational function for us. So let's see, we want to write and solve the following. So let's take a look here. For question number 1, it says the rate of change of p with respect to t. So anytime we see the phrase rate of change in ROC, this is telling us this is a derivative. So when we write this, we can write this as the change in p, which is dp. Remember, the d here really stands for delta. This is our symbol for delta in geometry, and we always meant that was the change in something. Well, the d is the same thing. It's like a delta as well. So it also represents the word change for us. So this is the change in p with respect to t. So dp dt. And then it says is, of course it is in mathematics, that's equals. And we say proportional to 10 minus t. So when we say proportional, this means that we are going to multiply by k. So we'll say this is k times 10 minus t. And today we're going to work on solving this. Let's try number 2 real quick. This says the rate of change of n with respect to t. So of course this is just going to be dn ds, with s not t, is proportional. again, this is going to be multiplied by k. So we're going to take that 250 minus n, and we're going to multiply by k. Now, if we were to separate the variables here, we're only going to bring over the 250 minus n. So this would be something like 1 over 250 minus n dn equals, leave the k ds. And we would solve that by integrating. Try the next one real quick. The rate of change of q with respect to t is inversely proportional. So remember, this is the one where we're going to divide. So it's going to be k over something. So it's going to be, and it's inversely proportional to the square root of t. So let's go and try it. This is the rate of change, so it's a derivative. dq dt is inversely proportional. So we're going to put the k on top, and on the bottom, we got the square root. And on the bottom here, we got the square root of t. So I'm going to put the square root of t down here. So there it is. That's how I wrote it. To solve this, we would have to bring, we want to solve for dq. Well, there's no q over here. Notice there is no q, so we don't need to put anything else on the left side. But we do need to bring the dt over. So let's go ahead and do that. So we would get dq equals k over root t dt. And let's go ahead and try solving this one. We would get dq equals, I'm going to write this as t to the negative half to put on top times k dt. When we integrate, I want to show you something here real quick. This just gives us q equals k times t to the 1/2 times 2 over 1 plus c1. And I want to show you something. You can leave it like this. That looks kind of messy. I'll clean it up a little bit. Q equals 2k t to the 1/2 plus c1. But I want to introduce you to my new best friend. This 2 times a k. This k is a constant, kind of like the c. So one thing I can do is this can be absorbed. I can just write this again as just k. 2 times k is just k. 2k is just k. We don't write down the k1 or k2. That's really only true for the constants, the c1s. So we get t to the 1/2 plus c1. So I can write it like this as well. There's our answer. All right, so for growth and decay, we're going to use the following model. Everything is going to be given this answer, y equals c e to the kt. The form dy dt equals ky is the differential form. And what the right side is saying is that we are proportional to the value. This is how half-life works. We have this is how, like I said, how half-life works. In half-life, we are saying we are proportional to half the amount of material. And we talked about this in pre-cal and in your science courses. Now, excuse me, if k is positive, we have growth, and if k is negative, we have decay. So let's take a look at an example here. The rate of population of yeast is given by a differential function. So they're telling us that this is indeed going to be a derivative where y of t is measured in grams and t is measured in minutes. The amount of yeast population increases according to our equation. dy dt is ky, where k is constant. At time t equals 0, the weight is 144 grams. So they're telling me this initial condition. So they're saying at t, the amount of material, which is y, so at t equals 0, we have 144 grams. And it's increasing at a rate of 24 grams per minute. Oh, so they're telling me right here, this is dy dt right there. That's my change. We want to find y of t. So if I start with my equation here, dy dt is ky, I need to find k. So I can do that by just plugging in. dy dt, they tell me, is 24. K I don't know. And let's see here. At time equals 0, the weight is 144, so I know that y is 144. Solving for k, now I'm going to cheat. I'm going to use a calculator here. So I'm going to take 24, can't you see this, divided by 144, and I get k equals 16. So I can say that dy dt is equal to K, which we said is 1/6 times Y. All right, so solving this, I can just bring the Y over. I get 1 over Y dy equals 1 over 6 dt. Integrating, so we get the natural log of Y equals 1/6 t plus C1. Exponentiate, we get the absolute value of Y equals e to the 1/6 t times e to the C1. And again, we're going to let e to the C1 equal just C2. And we get Y is plus or minus C2e to the 1/6 t. So once I'm here, I can now solve for C2. So we're going to find C2. Giving me the initial condition, which we said is right here, our initial condition. We have 0 and 144, but don't forget this is telling us that y is greater than 0, so we want the positive. So when we set this up, we would have 144 equals the positive C2 e to the 0, so C2 is just 144. So my equation, y would be 144 e to the 1/6 t. And what this does for us, there's our equation. So this equation tells us now is I can now find out how much yeast we have over in any given number of minutes. And we all start with just how it's changing over time. If we know how something is changing over time, we're able to calculate the value. Then that's what Newton's calculus does for us. All right, so we can come back for part 2 and take a look at some more examples. I'll see you then.